Hi everyone, just wanted to take a minute to talk a little bit about key features of quadratic functions. This is the start of chapter 8, so we are moving on to a new type of function. You will have seen these before at some point, most likely. It'll be functions dealing with squared values. All right, so let's take a minute and kind of preview this for ourselves. So when we're kind of looking here, this is the type of function we're going to be dealing with. F of x is equal to x squared. And as you can kind of see, there's already some similarities and some differences with the absolute value function. So when you're dealing with the quadratic function, which will be down here, you can see in general, it's going to start at 0, 0. That has a vertex of 0, 0, right? It's going to be increasing. It's going to have an axis of symmetry. But you will notice that, right, see here, we kind of had a linear rate of change. Here, our change is going to greatly differ, right? So, here it goes up, 2, or it goes up 4, and then it goes up a lot faster, right? So you can see that it kind of quickly is changing, and it has that more of a curved appearance. But there are a lot of similarities. So what you remember about absolute value functions is a good place for you to start off when you're thinking about this, right? So you are still going to be thinking about a vertex. You are going to be thinking about axis of symmetry. You are going to be thinking about increasing and decreasing. You are going to be thinking about the domain and range in a very similar manner. It's just the what's changing in particular is going to be your rate of change, really, right? All right, so what are our goals for this? We're going to describe some of the features, which I've kind of referenced already. And you're going to identify some situations where you could use quadratic functions. In particular, this topic, we're really making sure we understand the features a little bit less so than the some of the applications of it. Some of the applications come in once you get into more complex examples of quadratic functions, but we are going to kind of briefly get into those. So some words that we want to make sure we are aware of. We have a parent function. The parent function is going to be kind of like the simplest, the base case, if you will, of a particular family of functions, right? So we've seen it before. Y equals x is the parent function for the linear function, right? It's the line that goes through 0, 0. It has a slope of 1. It's kind of the simplest case, right? Similarly, when we were looking at exponential functions, our base case was 2 to the x, right? That was the simplest one that kind of had the features. Absolute value, f of x is equal to the absolute value of just the x, right? That was exactly what we saw. When we're looking at the parent function in terms of a quadratic function, it's just going to be f of x is equal to x squared, right? So you're only going to have the quadratic term, just x squared. There's going to be nothing special. When you graph a quadratic function, which, as I said, has the x squared, nothing bigger, it's going to be a shape called a parabola. And that's that kind of U shape that we saw before, right? We call this a parabola. And as we talked about, it'll have a vertex and an axis of symmetry, which you should recall from the absolute value, right? The vertex is the maximum or the minimum, right? Here's our vertex. And the axis of symmetry will kind of be the line of reflection. Okay. So when we're talking about quadratic functions, it's important to kind of look at it from the parent function perspective. So the parent function, as we said, was just x squared. It's going to be the simplest quadratic function in the family, right? It has all of the characteristics of a quadratic function, but it's the easiest to kind of work with, right? There's nothing added. There's no x term. It's straightforward. So as we saw before, the vertex is, again, in the base case, going to be 0, 0. I did, just as a reminder, again, this is called a parabola. So the base case is going to be 0, 0. For the vertex, the axis of symmetry is still going to be the x coordinate of the vertex, right? And as a reminder, the axis of symmetry is going to be the line that you're reflecting over. So, right, we go over here, same amount over, same amount over, same amount over, right? You could fold it and be right on top of itself. So once again, you're really only going to have to worry about finding these points. You count over from the axis of symmetry, you'll get the same picture. And again, you are going to have situations where it opens up or down. The parent function is always going to open up. It's not going to start opening down until you start putting things in front of it. All right. So one thing to consider here is, again, when you're looking at this table of values, as we talked about with the axis of symmetry, you can more clearly see that if you go to the right one, you go up one. If you go to the left one, you go up one, right? So if you're 1 to the right or left, you go up the same amount. If you're 2 to the right or left, you go up the same amount. Similarly, if you go 3 to the right or left, you're going up the same amount. And why is that? Well, you'll probably think about this, right? So f of x is equal to x squared. So the reasoning behind that is if I look at, f of 3, right, that's 3 squared, which is equal to 3 times 3. But if I look at f of negative 3, that's negative 3 squared, which is negative 3 times negative 3, which is still 9, right? So no matter what, because the negative is inside the parentheses, you're going to square it. So it's always going to be positive. All right, so that's why it doesn't make a difference if you go to the right or to the left. They're going to go up the same amount. All right. So if you kind of think about it, in general, when you start off, you're always going to be positive. I mean, you are going to be at 0, 0 at one point, which you really wouldn't describe as positive. But outside of that, it's going to always be positive. Because it's always going to be positive, your general situation, right, is going to have a range of greater than 0. Well, greater than or equal to 0, I should say, because you are including 0. And your domain, as we talked about, because you can put in any number and get out an answer, your domain is once again going to be negative infinity to infinity. Now, what happens if I put a number in front? Guess what? It's time for sliders again. So now we're going to put an a value in the front, and we're going to see how that affects things. So I'm just going to open up our slider here. So we're starting off with our, once it loads, we are starting off with, here's our parabola, right? Our function f of x equals x squared. The purple line is going to be the one that shows you the parent function. And you're going to see what happens when I start changing a. So I'm going to make a bigger. And you can already see the red, which is G here, where it has the A infecting it. As A is getting bigger, right, it's getting closer and closer and closer into the y-axis, okay? And then similarly, if I get less than 1, you can probably already guess what's going to happen. It's going to flatten out, all right? So here we have when a is less than 1, we're going to have vertical compression. All right? And when a is bigger than 1, we're going to have a vertical stretch, right? Because we're stretching it up towards the towards the y-axis. We're compressing it down away from the y-axis when it's smaller. Okay? So right, when you have an a that's less than 1, you're going to have a wider. And when you have an a that is greater than 1, you're going to have a skinnier kind of parabola. Now, if I make it negative, you can probably already guess what's going to happen. It's going to flip over. And then once again, if it is bigger than -1, or I should say less than -1, it's going to get skinny. And when it's between -1 and 0, it's going to be very wide, right? So we're still going to have that same thing where if it's between 0 and -1, it is going to be compressed, vertically compressed, and if it is greater than less than -1, I guess you should say, it's going to be vertically stretched, right? It's getting closer and closer to the y-axis. All right. So how is that going to affect the domain and range? Well, obviously, as you can see here, in general, the domain and range, as we said, was negative. The domain was negative infinity to infinity, all right? And the range, domain, right? This is in general what we're going to have. And my range, we go from 0 up to infinity. Now, if I make my a negative, oh, you know what? Before I do that, here it is at 1. If I make it less than 1, my domain and range don't change, right? I'm still going to have that. If I make it greater than 1, my domain and range don't change. The problem is when I make it negative, it will change. The domain won't, right? The domain is still, I can still put in any number. But the range will change, all right? So now it goes up to 0 from negative infinity. Okay, but it still is including 0 in this case. So you do have to be careful, right? The domain and range, the domain is never going to change, but the range will indeed change, depending on whether or not you have a negative out front. All right. You probably would have guessed that. Right? It's exactly what we did with absolute value functions. A lot of the concepts are the same. The only thing that is different is going to end up being kind of if you're looking at the rate of change. So how do we actually know, or what do we know about the value of a based on this picture? Right, so we have a really skinny one, so you know it's going to be, a is just going to be greater than 1. I don't know what it is, right? I don't know what it is when it's like this, but I know a is greater than 1, right? The blue line being the original one. Now, what do I know about this? Well, it's upside down, so you already know it's less than 0, right? It's going to be a negative number, but it's skinny. It's a skinnier one, which means it's going to be, in particular, less than negative 1, right? If it was kind of wider, you know it'd be between 0 and negative 1, but it looks like it's a lot skinnier than the original picture. All right. Now, once again, if we talk about increasing and decreasing, the same rules are still going to apply. It is going to change at the vertex. So it's going to be if we go back to our picture, here, right, in the parent function, or when a is bigger than 0, it is decreasing until 0, and then it is increasing after 0. When a is less than 0, when a is negative, you're going to be increasing to 0 and then decreasing after, all right? So that's the only thing that's going to change. But a lot of the information, again, it's exactly like you saw with the absolute value functions. All right. So, for example, if we're looking at this, we know it's increasing when it's less than 0, and it's decreasing when it's greater than 0. So what's a possible value for a? Well, basically, what are we saying here? We're saying if we have a graph, it is increasing over here and decreasing over here, right? So that basically is going to tell us that a is less than 0. I can pick any number less than 0, doesn't matter. It does have to be less than 0. It can't be 0. A is 0. That's just 0, right? That's not a parabola. All right. Now, I do want to quickly talk about a couple of examples in terms of applications. Pretty much at this point, all we're going to be looking at is things relating to area, right? Because if you look at it, right, f of x is equal to x squared. What is that? This is essentially the area of a square, right? So when you're dealing with these, you're just going to be looking at it in terms of areas of squares. Now, last thing I do want to talk about, if you're having to compare the rate of change of different different quadratic functions here, one important thing to consider is going to be the bigger the a value, the greater the rate of change, which makes sense, right? Now, you probably have to remind yourself, well, how do you calculate rate of change? So rate of change on average is going to be calculated using this. F of x one minus f of x, right? So essentially you do f of 4 minus f of 2 over 4 minus 2, right? That's what you're going to do. So you're going to go through this process. You plug it in, you evaluate it, it's 12, 3, 4, 2, right? 24, 6, 4, 2, right? So when you plug it in, you'll find that when you have a bigger a value, you're going to have a greater rate of change, which makes sense, right? If I took my function and I multiply it by a bigger number, of course I'm going to get a bigger answer. And if you're multiplying a bigger answer or a bigger number by a bigger value, you're going to get a bigger value a lot faster. So that kind of makes sense. All right. So we're going to continue on and talk more about this going forward, but this should hopefully be a nice overview of some of the features of a quadratic function. Let me know if you have any questions, and have a great day.